Hi guys, so today I'm going to be going over my combined spectral problem solution. I was assigned the group 1 molecule, so I will go ahead and show you how I was able to solve for my proposed structure. The task at hand was to analyze these 3 spectrum graphs and determine a proposed final structure for our molecule. We were given the molecular formula of C6H12O2. Each graph is labeled with which type of spectrum it was to help identify them better. So the first task I needed to complete was to solve for the DU value. The DU is the degree of unsaturation, which is a calculation that determines the number of pi bonds and/or rings within a molecule. In the first image is given the formula for finding the DU value. So it is 2C plus 2 plus N minus X minus H all over 2. The C stands for the number of carbons within the molecule, the N stands for the number of nitrogens within the molecule, and the X stands for the number of halogens within the molecule, and the H stands for the number of hydrogens within the molecule. The next image shows once our values are substituted into the equation. So the 6 is the amount of carbons we had in our molecule, and the 12 is the number of hydrogens. In our molecule, we did not contain any nitrogens or halogens, so those were negated from our formula. We were left with a value of 1, and this was able to represent that our molecule will contain a double bond within our structure. The next thing I looked at was the IR spectrum. So in the spectrum, we were able to determine 3 major peaks. The first peak that I want to talk about is the one that sits between 2,950 and 2,850. This we were able to determine as the CH functional group. And so we were able to determine this because the IR spectrum looks at bond strength, bond type, atom mass, and more. So within the CH, the hydrogen atom is lighter than oxygen atoms, allowing the CH to vibrate faster, giving it an increased frequency in the spectrum. When looking at the other 2 peaks, the COO at 1750 was actually a higher frequency than the single bonded C to the O, and this is because the double bond is stronger and stiffer, essentially acting like a tight spring, allowing for increased vibration and absorbance of higher frequencies than the looser single bonded structure. So the CH was identified as an alkane chain, the C double bonded to the O was identified as an ester group, and the C single bonded to the O was identified as a stretch. A stretch is pretty much just a continuous chain in the distance, a continuous change in the distance between 2 atoms along the bond axis. In our next spectrum, we looked at the 13C spectrum, and this spectrum looks at the chemical shift values of the peaks. So for every signal, there is a unique carbon that's being measured, and it's measured in parts per million. So the chemical shifts on this spectrum are going to be caused by electron density around the carbon nucleus, which is influenced by the electronegativity of neighboring atoms, the hybridization state of the carbon atom, and the presence of nearby functional groups leading to the de-shielding effects, lowering electron density and causing a downfield shift This will all result in a higher ppm value, that parts per million value. So going into our chart, the first chemical shift noted is the one at 174 parts per million. This was identified as the carbon double bonded to the oxygen. This shift is due to the highly electronegative oxygen atom. The chemical shift at 62 parts per million was identified as the oxygen single bonded to a CH2. The shift is caused here by the electron withdrawing effect of the oxygen atom. When looking at the two CH2 groups that were identified, the one that has a chemical shift of 36 parts per million can be attributed to the oxygen atom again, meaning that one of the CH2 groups is going to be more closely bound within the molecule to the oxygen atom, causing that shift, increasing the parts per million. Both the CH3 groups were pretty low in value and very similar. That brings us to our last spectrum to look at, and that is our 1H spectrum. And so this analyzes the number of hydrogen types within the molecule. It will look at varying electron densities around a hydrogen nucleus, leading to different levels of shielding from the magnetic field. The more shielding there is, the lower the chemical shift will be. So within our chart, we can see here that there are only 5 shifts noted, whereas in the 13C spectrum chart, there were 6 shifts noted. That is because there is a C double bonded to an O within our structure containing no hydrogen atoms. Therefore, it will not be picked up on this spectrum. So to talk a little bit about what we are seeing here in our chart, the chemical shift at 4.1 is said to have 2 hydrogens. Its multiplicity is a quartet. This means that it will have 2 hydrogens and will have 3 neighboring hydrogens. So as you can see in our interpretation, since it does have a higher shift, it is bonded to that oxygen, causing that de-shielding effect again, but also bonded to that CH3, allowing it those 3 neighbors. The second shift we look at is the 2.3 shift. It also contains 2 hydrogens, but has a multiplicity of a triplet. This means that it has 2 hydrogens again, but only 2 neighbors. You can see in the interpretation, the shift is still caused because it is closely bound to an oxygen atom, but not directly. And it has those 2 hydrogen neighbors. The third shift we look at is the 1.7 shift. It contains 2 hydrogens and is a sextet, meaning that it will have 5 neighboring hydrogens and still contains 2 hydrogens within this atom. As you can see in our interpretation, it means that it is bound to that CH3 group as well as a CH2 group. The next shift is a 1.1 shift, and the one after that is a 0.9. Both of these contain 3 hydrogens and are both triplets, meaning that they have 3 hydrogens within their structure and they both have 2 neighbors. However, the slightly higher shift within the one can be attributed to the fact that it is more closely bound to an oxygen than the other. So overall, that really helped us visualize how our structure is going to be bound together. And for our final results, you can see that the molecular formula was C6H12O2. The structural formula was CH3, CH2, CH2, COO, CH2, CH3. The molecular name was ethyl butyrate, and the proposed structure is drawn down below for you. Thank you for listening. I hope you had a good time learning.